Let's look at one more type of regularization, and this is called elastic net regression. So this is the case where we apply two regularization terms, both a one norm and a two norm regularization term. So another way to think of this is that our prior over W is a mixture of Gaussian and Laplace. So there are a couple of advantages to this. So the first one is that some of those issues that are introduced with lasso, elastic net doesn't have, specifically with regard to strong convexity and optimization. So recall that our lasso objective has these kind of straight sides, meaning that it's not always strongly convex, which can make optimization harder. Adding this additional L2 regularization term kind of softens those edges. Let's draw it bigger so that we can see this. So we still end up with a sharp tip that's non-differentiable, but our curve kind of bows out like this, and it is always curved up, meaning it's strongly convex, which can help with optimization. Reason number two, this is valuable. So let's imagine the case where we have two features that are very strongly correlated with one another. That is, they're high in the same set of examples and low in the same set of examples. What's going to happen if we apply just L1 regularization to that problem? Generally, what's going to happen is, again, the model likes sparsity, and it's not too hard to see. You can see this by looking at by kind of imagining the objective and looking at the updates, is that usually what's going to happen is that it's going to set, the optimization is going to set one of those features to have a high weight and the other feature to have 0 weight. So this is not so good, especially if you're interested in which features are chosen by the model, because the model says that the second one is not predictive and the first one is predictive, even though the model could have swapped those weights and ended up with almost identical performance, just maybe very slightly less. So what's going to happen with elastic net regression? So again, just to draw that, it might look like this. If we have W1 and W2, L1 is going to choose, let's say, W1 to be high and W2 to be 0 generally. Now, elastic net regression, if we add both this L2 and L1 term, notice that the strength of penalty for each parameter in the L2 case grows as the value gets higher. So in that case, it's not too hard to convince yourself that if W1 and W2 are very well correlated, we're going to end up with nearly the same weight for both. And generally they're going to be they're both going to get a non-zero weight. So again, this is valuable. It gives you kind of a more honest view of the results of your feature selection, that it is not going to choose one arbitrarily, instead it's going to choose both. So elastic net regression, why is it called elastic net, by the way? It's because it's like lasso, which is kind of like a net. A lasso is a name for like a rope that you use to capture an animal, I guess, like a cow. But it has this kind of, this additional kind of L2 weight, which is kind of stretchy. So in that sense, it's elastic. there's your reason it's called elastic net. So again, elastic net is just this combination of the L2 and the L1 regularization, and it's very often a good thing to do. I would say probably if you're doing most problems, in most cases, it's useful to have some form of regularization. If you're interested in feature selection, you want at least part of that regularization to be L1 regularization. If you're going to have some L1 regularization, usually it's the right thing to do also to have some L2 regularization. We're not going to talk about how to do that optimization. That's a candidate for your assignment. I think that's going to be one of the assignment questions. You'll see that it's not too hard to do elastic net regression, or at least it's not too much harder than the lasso optimization itself. Okay, so that was our discussion of linear regression, where really we were mostly using linear regression as kind of a test bed example with which to explore the various ways we can add regularization or priors to influence various things about the results of our optimization. So I just wanted to, in one slide, compare those different methods we talked about and with regards to how they might do feature selection. So let's look first at just our unregularized maximum likelihood estimate. That sets our W's to this ratio we saw before, CD over AD. Again, those are defined on that previous slide. One way to compare these different methods is to look at what they do to those weights. So we didn't show this here, but it's not too hard to show that our ridge regression, that is L2 regularized linear regression, Gaussian prior, gives us this ratio, our MLE estimate divided by 1 plus lambda. So our ridge regression is kind of shrinking all of our parameters like this. By the way, one thing that's important to note is this is what happens to the updates. And when we update one parameter, that's going to influence the update of another parameter, and so on until we converge. So it's not like we train our linear regression parameters and then at the end apply these different regularization fixes and just sort of blindly, in the case of ridge regression, divide. So applying ridge regression on one parameter is going to influence another parameter. So it's not like you're going to get the same parameters, but with this division. But this is what happens in the update. And so this is one, I think, useful way to understand the distinction between these different methods. Vice versa, our L1 lasso, that has this update. We take our weight and we reduce its magnitude by lambda. And then if that if our weight had low enough magnitude to begin with that we end up with a negative number, we just set it to 0. That's what this plus notation means. It means it's this value, but only if it's positive, otherwise 0. And then we add back the sign because we had taken the absolute value here. So here, this is another way to understand the distinction between our L2 and L1. L2 is dividing our parameters, where L1 is subtracting from our parameters. Then we might compare that to a very simple strategy where we just do a subset selection of our features. That is, we just rank the features by their magnitude and choose the top k and set all the rest to 0.